Hello students, in this video we'll continue our discussion with chi-squared random variables. Recall from our last video that z is chi-squared with n degrees of freedom if z is equal to x1 squared plus xn squared, where the xi, x1 through x1 through xn are IID normal 0, 1 random variables. Okay? And we saw previously that if z1 was chi-squared 1, then this was exactly the same distribution as this was exactly the same as gamma of 1/2 comma 2. Where remember what gamma random variables are. Gamma random variables have this property that gamma of alpha and theta have PDF x to the alpha minus 1, e to the negative x over theta, theta to the alpha, gamma of alpha, and this of course is valid if x is greater than 0. So those are our gamma random variables. And it turns out that we've seen previously that the MGF, moment generating function, of these gamma random variables is equal to 1 over 1 minus t theta to the power alpha for t less than 1 over theta. T less than 1 over theta. Right, so this is the MGF at t for a gamma random variable. Now what I have here is I have the sum of a whole bunch of what? I have x1 squared plus x2 squared plus x3 squared plus xn squared. That's the sum of exactly n of those random variables, which are all chi-squared with 1 degree of freedom. So I can say that the MGF of z, in this case, so the MGF moment generating function of z is going to be equal to what? Is going to be the product of the MGFs. Product of MGFs of each term. So what it tells me is that says that the MGF of g is equal to what? It is equal to 1 over 1 minus 2t, because it was my parameter of theta was 2 from a previous video. And then I have a what? Then I have a 1/2 power in the denominator. That was my alpha, was 1/2. And I'm going to multiply this by itself exactly n times. 1 minus 2t to the power 1/2. So what do we have over here? Now each of these is common. So this is 1 over 1 minus 2t to the what? There's n copies of this, so I'm going to have an n over 2. And this, of course, is the what? This is also the MGF moment generating function of what? Of a gamma distribution with alpha equals what? With my alpha equals n over 2 and my theta equals 2. So we've just shown that chi-squared distributions with n degrees of freedom are gamma distributed with the alpha parameter being n over 2 and the theta parameter being equal to 2. So from this we can actually get lots of results about these chi-squareds. So in particular, we know the following. So for gamma alpha theta, if we have a random variable that's in this class, let's say that random variable is y, so if y is in that class, then we know the expected value of y is alpha times theta. And then we know that the variance of y from properties of the gamma distribution is going to be theta squared times alpha. That's the variance of y, is theta squared times alpha. So, good. So now what? So now we can translate these properties to the properties about the chi-squared. So the expected value of a chi-squared distribution with n degrees of freedom will be what? Well, it's going to be my alpha times my theta. So if a random variable has chi-squared distribution with n degrees of freedom, its expected value is n. Its variance of a chi-squared distribution with n degrees of freedom will be equal to what? My alpha is n over 2, and I do theta squared. So I'm going to have a what? I'm going to have a 2 squared, so that's a 4, times my alpha, which is n over 2. So let's get a total factor of what? Of just 2n. So the variance of a chi-squared is 2n. And this provides us with enough information about chi-squareds to start to prove results about sample population variance. Thank you very much.